If you are new to the channel, then subscribe the channel and press the bell icon for further notification. Okay student, welcome you all to this new lecture in Power System Gate series. So today again we will be solving 5 questions starting from question number 141 to up to question number 145. Okay, then let's try to solve these questions. Okay, in question number 141, a 100 MVA 11 kV 3 phase 50 Hz 8 pole synchronous generator has an inertia constant H equal to 4 megajoule per MVA. The stored energy in the rotor of the generator at synchronous speed will be. So what will be the stored energy? 4 megajoule per MVA. So it is 100 MVA. So you can easily find out stored energy will be 4 into 100, that is 400 megajoule, which is your option B. That is 400 megajoule. Next, if you come to 142, the use of the high speed circuit breaker. Now we have already seen the use of high speed circuit breaker is to increase the transient stability. Let's read one by one which one is the best suitable. That one will give the answer. It reduces the short circuit current. There is nothing related to your short circuit current limit with circuit breaker. That short circuit current depends on the reactance that is in the path where the current is flowing. So it neither reduces nor increases the short circuit current. So A and D, you can see, increases the short circuit current, reduces. So it is obviously not A and D. Now next, it improves the system reliability. Okay, it improves system reliability, but let's see whether other better choices we have or not. In such questions, you have to take the best and possible answer, that is. Next, decreases the system stability. No, it doesn't decreases, it rather increases the transient stability. So obviously we have left with option B, which improves the system reliability. Means if there is a fault, then the faulty side will be isolated very fast, so that the system will not be under pressure, and the system will run in smooth operation with the rest of the systems. So that's reliability. That's known as reliability. Every time your power will not go, you will get a reliable power. Wherever there is a fault, that side will be isolated very fast, so that on the system there is no effect of that fault, and other parts remain healthy. So that's why 142B. Now if you come to 143, an alternator is connected to infinite bias as shown in the figure. It delivers 1 per unit current at point 8. So what is the current they have given? Point 8 lagging. V is, this one is given. The reactance is given. Determine the active power output and the steady state power limit. This one first, then next line, keeping the active power fixed. If the excitation is reduced, find the critical excitation corresponding to the operation at stability limit. Okay, if you see this one, this generator is sending power to this one. In between there is no resistance, so whatever there will be no active power drop. So whatever P it is sending, same P it is receiving. So what is the power it is coming here? I told you, if you have this bus voltage and this bus current here, so what is the power current here? This V into I star. This V into this I, that is the power coming here. So S is equal to Vi star. So if you do this one, that is V is 1 angle 0 and I star, what is I? 1 at an angle of minus 36.86 star. Why 36.86? Because it is cos inverse 0.8, that lagging power factor, which is 36.86. So you know the angle with which it is lagging the voltage V. So if you do this one, you will get it 0.8 plus 0.6 J. That means active power that is sent by this generator to this side, that is received by this bus. In between there is no loss. If there is loss, then we could not have said that this is 0.8. This one 0.8 receiving plus loss will be this one. But there is no active power loss, no R is there. So the power that is sent, the first answer, that is power sent, is 0.8. That is the active power it is sent. Active power output, P output. Now they are asking the steady state power limit. For steady state power limit, what is the P max? That is magnitude of V by XD sin delta. Okay, so they have given you XD, that is 1.2. E you don't know, so E you can calculate. This current plus this voltage plus this drop will give you this one, E. So E angle delta is nothing but 1 angle 0 plus I into I is my 1 angle minus 36.86 into J 1.2, this 1.2. So if you do this one, you will find it is 1.9696 at an angle of 29.173. So you put it there. E is equal to 1.9696, B is 1, and then XD is 1.2, and then sin delta is 29.173. So if you do, it is the maximum, that is 1. This is another answer. The second one, steady state power limit. Now they are saying the third one, keeping the active power fixed. Now active power should be 0.8, this output. That is E into V by X sin delta, that is fixed, 0.8. Find the critical excitation corresponds to the operation at stability level. What is critical operation? Critical operation is delta equal to 90, because this is the maximum limit you can go. So this is critical operation. So you have to calculate what is the maximum excitation reduction is possible. So that means you have to calculate E. So this is sin delta I have taken 1, because critical point it is 1 and it is 0.8. So if you solve it, you will get E is equal to 0.96. That means this is the excitation level. You can bring it down so that it doesn't affect your steady state limit. It is the maximum limit that it can go. So maximum this much you can reduction possible. So this is another one. So 3 answer is there, 1, 2 and 3. Now if you come to question number 144, a power system consists of two synchronous generators A and B, rating 250 and 500 MVA, inertia is 1.6 per unit, 1 per unit respectively on their own base MVA rating. So 1.6 on 250, 1 MVA, 1 per unit on this one. This is the inertia. The equivalent per unit inertia constant for the parallel system 100 MVA. So what will be the total inertia here? 250 into this, 500 into this, divided by you want to go at 100 base. So you have solved this type of questions before also. So the first one, inertia is 1.6 per unit on the basis of 250. Second one is 1 is into 500 divided by 100. So if you do this one, it is 9 per unit. That is option D. Next, if you come to 145, the load carrying capability of a long AC transmission line is always limited by conductor size. No, this is not how much current it can flow. This is actually depend on the stability consideration. This one, first we consider the what is the steady state stability limit, how much maximum power we can throw. Once we calculate that power, on the basis of power we calculate how much current it will take, and then on the basis of that we decide the size of the conductor. So the load carrying capability is mainly depend on the stability consideration. On the basis of that we calculate the P max that we can pass through that line. On the basis of that P max, we calculate that what should be the conductor size. So it is not depending on first conductor size. Then because my conductor is small, so I will send small. Because my conductor is big, so I will send big more power. No, it is depends on the stability. System should be stable also. Reduced at low, decreased the use of the bundle conductor. No, so it is obviously limited by the stability consideration. That is 145B. If you like the video, then press the like button and please give your valuable comments in the comment section.